Hey, good afternoon, everyone. My name is Karthik Bharti. I'm the product manager for Amazon Neptune. And joining me today are our customers, Elliot Foster, software architect from NBC Universal, and Yash Shunar, software engineer from Uber Advanced Technology Group. In the next 60 minutes, we'll be talking about the use cases for Neptune, and our customers will walk you through their experience with using Neptune, learnings, and some of their experiences in their journey using Neptune. As a takeaway, at the end of the session, you will be aware of the set of use cases Neptune is targeting, and hopefully that motivates you to try out Neptune. Just a quick show of hands, how many of you in the audience are using graph databases today? Okay, that's a good turn. How many of you are using Amazon Neptune in production today? Okay. And how many of you contemplate on using Neptune in the next 3 to 6 months? Okay, that pretty much is, you're the right audience for this presentation. As a quick background, graphs are ubiquitous. If you've used any of these applications in the last day, hour, or even a week, chances are these applications are being powered by graph databases. The search engine that you're using, the professional network or the social network you're using, the travel that you booked to attend this conference, the different speakers and sessions that you're talking to when you're attending, and the devices, the different devices you hold in your hand are all applications that will use graph databases. And it's no surprise that the internet is one big graph, right? You have servers, machines, websites, interconnections. It's a graph network. You ask anyone how to draw this, and you'd probably see circles and lines, and that's essentially a graph problem. So what we did was we looked at all of these applications, and we distilled it to about 6 use cases based on our customer interactions. And there are many more use cases that we can talk about, but these are the 6 main ones that we look at. If you look at social networking, a company, Nike, tracks user interests against players and the products they buy, and that's available as a mobile application. That's an example of a social network. Thomson Reuters, they map graph with the set of tax policies that change across different countries. And when an organization wants to go into a new region, it can recommend the set of tax policies that apply to that company. Siemens is another great example of a knowledge graph. They have data that's distributed across different locations and teams, and they build a knowledge graph using Neptune. Fraud detection is another great example, primarily in financial services. And PaySense is a great example of customer using Neptune for fraud detection today. Life sciences, another broad area. Blackfin is a great example. So Blackfin looks at clinical trials, sort of the test hypothesis, and this generates a lot of metadata. And they model this metadata using a graph database. Another customer who's been successful with Amazon Neptune. And finally, in the network and IT operations use case, we have internal customers who look at the set of devices, the storage, router, servers, and sort of use a graph to assess the dependencies. So if, let's say, a router should go down or perform suboptimally, then what are the set of other related resources that would be impacted, right? So in a sense, Neptune is really all about managing your relationships in your connected data. And which is exactly why we built Amazon Neptune. Amazon Neptune is a purpose-built graph database, and it's fast, reliable, open, and very easy to use. Why is it fast? Because you can store billions of relationships, and you can query them within a matter of milliseconds. Why is it reliable? Because we talk about the shared cloud-native storage, and what we do is we have the notion of segment, which is like a 10 gigabyte data unit, and that is being striped across 3 availability zones, and you have 6 copies in total. That makes it really reliable. Should any one of the AZs goes down, Neptune is still fault tolerant, so your application continues without any impact. You're already aware that Neptune supports both the Apache Tinkerpop property graph model and the W3C resource description framework. Both these standards are supported. And the corresponding languages, Gremlin and Sparkle, that makes it easy to use. And these are open standards. By any means, you can plug into it. If you have an existing application, you can integrate it with Neptune. Now, there are a set of features that we introduced in the last 3 months, and this is a growing list. And every month I look at this and say, oh, I need to update a couple of rows and just add new features to this. Of this, I would call out the last one, the Neptune Workbench, which we announced at reInvent, and it's live for all customers yesterday afternoon. Neptune Workbench is an in-console query experience to query your graph database using Jupyter Notebooks, which is very familiar to developers. And the Workbench experience is available in all the commercial regions that Neptune is available in. And for the other features, I would highly recommend you refer to our deep dive session where we covered many of the other features, and even we had demos around those. Switching gears a bit, here's the list of customers that are using Neptune today in production. And we talked about many of these when we were looking at use cases. Of this list, we're going to focus on 2 customers today, NBC Universal and Uber ATG, like I called out. NBC Universal has an interesting use case. So they had a NoSQL database, and they went through the journey of moving into Amazon Neptune. And Elliot is here today to talk us through the use case. And as he talks through the use case, pay close attention to some of the benefits that they saw, and I'll come back and talk to you more about it. Over to you, Elliot.
Thank you, Karthik. I'm Elliot Foster. I'm a software architect from Four Kitchens and tech lead on NBC's backend team. Four Kitchens has been partnered with NBC since 2013. And our backend team consists of 11 engineers from 6 US states and 2 countries. So our story begins in spring 2018, and we had some problems. Our data was stored in a document store, but accessed and modeled in a highly relational way. Users watch videos. Videos are parts of series and seasons. This can scale, but it didn't for the way that our data was stored. Additionally, we were seeing substantial year-over-year growth and a focus on highly personalized data. So caching strategies were either ineffective or not scalable. Operationally, the legacy store was managed in-house. This was expensive and required a lot of resources from the internal operations team to maintain. And all this was made worse because of the traffic pattern that we see. Our traffic follows a traditional TV model, where in the early part of the day, there's not much going on. As you get closer to prime time, traffic ramps up, and then it ramps back down later in the day. Given the way that our legacy store was set up, there was a lot of operational resources involved in scaling up and down. So we typically ended up being over-provisioned. Long story short, we knew we could do better. So my team set out to find another solution. And we vetted several alternative databases, including other document stores, relational databases, and ultimately graph databases. We felt confident that graph databases would give us the level of scale and that it was really the right tool for the job. Around this time, Neptune had just been announced, but it wasn't yet in GA. So we worked closely with the team from AWS to build out a prototype. And there were definitely some growing pains, as there always will be with a new product, but we saw enough to know that this was a solution that was going to work and fit our needs. I think it's important to note that at this point, the product is much more mature. The documentation is there. We would have been able to do what we did today without as much support from AWS that we got, but it certainly was very helpful. Initially, we considered Neptune, or another point that we were considering Neptune was for its support of Sparkle. Our legacy database was queried out of Sparkle, so we were hopeful that we could take the queries that were already written and apply them straight to Neptune. It turned out that for our use case, this was actually not as performant as we would have liked. But when we moved to Gremlin, things were much, much faster. Additionally, Gremlin's a lot more user-friendly from a developer standpoint. In the legacy system, there were maybe 2 engineers on the team that understood Sparkle well enough to write complicated queries. And at this point, almost every single engineer on the team can write complicated traversals. So we set about doing our migration. Migrating such a fundamental piece of your stack is hard. The business would not tolerate a major outage, and move fast and break things probably would have gotten us fired. Additionally, we're in the middle of the largest change to the content in the system that we've seen since we started this project. It's an initiative we call One App, and it was the introduction of the rest of NBC Universal's content into our system. So instead of just having NBC shows, now we have E! And Bravo and Telemundo, et cetera. It resulted in about a 10 times increase in the amount of content that we were responsible for. So the approach we took was building out components and releasing them in production in parallel with our legacy system. And this was hugely beneficial because we could see how the Neptune back system was behaving with the same amount of traffic, the same amount of throughput, the same everything that the legacy system was doing, and we could confidently say when we were ready to roll things in production. And this is kind of what we came up with. Each path in this diagram is sort of one phase of our migration. The first phase involved users. This is by far the highest throughput area of our stack, but it's also the simplest graph. So during this phase, we learned a lot about how Neptune scales, how to provision it, what are the gotchas around that sort of thing. The traversals we were writing at this point were very simple. The second phase of our migration involved getting all the video content and all of that metadata into the system. And at this point, our traversals became more complicated, but they were mostly based on insertion. And it was at this point that we started to write a custom traversal builder. And we built this on top of our actual JSON schema data model. So the way that an entity is defined for an end user was decorated with metadata that we used to actually build the traversals. We took that pattern and applied it to reading the content back out. And this allowed us to have a system where we could repeatedly and reliably build traversals as we introduced new members to our graph. And this is what it looked like from a performance standpoint. Each point on the graph is sort of a snapshot of where we were at a point in time. And so as you can see, when we started, we were at an average response time of about 230 milliseconds, and we're seeing about 20,000 requests a day. And this, it's important to note, these are numbers from the system that is fronting the database, so you can see the effect that Neptune is having as we progressively migrated. During our first phase, when we introduced the users, we didn't see a huge difference in response time, and this is primarily because we front the interactions to the database with Kinesis. So we were already pretty performant, but there was a small drop. Second phase is when the content is in, and we started to write custom traversals, and you can see a pretty substantial drop, down to about 122 milliseconds. And you can also see the request per minute was growing during this time. So although we had more throughput that we were serving, we were doing it much faster. And finally, during our third phase, this is about when one app went live. So you can see another very large increase, but we were able to get our response time out of the system down to about 40 milliseconds. So by migrating progressively to Neptune, we saw about a 6 times speed increase, while we saw nearly double the amount of traffic. So where are we today? We're done. No, we're not. So that previous graph really highlights in a very visual way where we were at. But some of the benefits that aren't as obvious are on the operational side. Neptune has been much more reliable than our legacy system. There have been a couple of failovers, but when it happens, the amount of time that operations spends dealing with that is much less. And the actual effect to the whole system is minimal, if at all. Additionally, it's much cheaper to run the Neptune cluster than it was our legacy system. And this is primarily because Neptune is much more performant than our legacy system was. So we need fewer servers. And really, we are just starting to scratch the surface of what we can do with Neptune. So here are some things that we learned. One thing that was real hard for us to wrap our heads around at first was that it's easy to write a traversal that brings back most of, if not all of your graph. And in a relational database or a document store, that's usually not a big deal. But given the way the graph databases behave, it really is a big deal, and it's not something that you can take for granted. We've had success in using techniques such as hypergraphs, where we denormalize information into our graph. So we can pre-compute things, make that part of our graph, and then use those computed values to write more performant traversals. You can kind of think of them like indexes in a more traditional SQL model. Additionally, due to the cluster having a single writer, you have to be careful about how you're provisioning your cluster. As I mentioned, write throughput is a substantial part of our use case. So and as a result, the writer needs to be sized much larger than the readers do. But if that writer falls over and you don't have another member of your cluster that is provisioned at the same size, you end up in a situation where you're severely under-provisioned. That wasn't obvious at the time. Again, documentation around this stuff is a lot better than when we started. So, yeah. And finally, using our data model, tying the way that we were writing our traversals to the way that we were actually defining the data has been hugely successful. And it's prevented drift from everything from documentation to the way that we are building out our applications. And it has allowed us to write repeatable and reliable traversals. So from here, the data science team at NBC is extremely excited about the personalization aspects and deeper insight into how users are interacting with our data. Currently, a lot of these things are calculated offline. They're querying one system, moving it to another, running some queries, and then sending it back to us. By having all this information in our graph, we're in a position where we can run these things closer to real time. Additionally, we'd like to build out a GraphQL API, a GraphQL to Neptune API. Currently, we do have a GraphQL API, but it is just fronting a REST API. So being able to remove that middle piece would be highly beneficial. And with that, I'll hand it back to Karthik.
Thank you, Elliot. That was a very insightful use case. As Elliot was talking, I noted 3 takeaways. Right? One, as they were migrating from their NoSQL database to Neptune, it was a progressive migration. It was not a one-time lift and shift and saying, hey, here's my data. Right? And as part of that progressive migration, they had to do the POC, and they also had to have a live system of Neptune and the live system of their existing database and make sure, capability and performance-wise, Neptune was able to meet. 2, Neptune provided the flexibility of Gremlin and Sparkle, and they had the choice to say, hey, what should I go with for my production use case? And 3, as they started moving more and more workload to Neptune, you saw that yellow graph and the blue line. They had more number of operations on Neptune, but at the same time, the query latency was in the order of few tens of milliseconds. So those would be the 3 takeaways for me when I listen to Iliad. Now, let's switch gears. We talked about how customer moved their workload to Neptune. Now let's look at how Uber Advanced Technology Group runs Neptune at scale. And for this, I invite Yaz to walk us through their use case.
Hi, everyone. I'm Yaz. I'm a software engineer at Uber ATG. ATG stands for Advanced Technology Group. ATG stands for Advanced Technologies Group. We are Uber's primary driverless car subsidiary. We're talking a little bit about how we handle map versioning at scale. We're going through 4 things: map versioning at ATG, map versioning as a graph, map versioning in Neptune, and map versioning at scale. Now, I know what you guys are asking. What is map versioning? So when you want to send a driverless car out, it needs to have a pre-mapped area of wherever it's driving. This is the difference really between an L4 and an L5 car. And so Uber is currently doing mapping in places like San Francisco, Dallas, Pittsburgh, a few other cities, so that we can run tests and get driverless cars out there. One of the things we quickly found is that our maps needed lots of edits. And after a few years, even thousands of edits. So what you can see here is a small graph of all the edits that occurred in one major city, with each tiny, tiny dot referring to a map version. That's a complete map. See, that gets pretty big pretty quickly. Now, you take something like that, you've got X number of versions, you've got Y terabytes per map, you're going to have to scale your S3 usage and your S3 costs very, very quickly. And so we know we needed a solution on our own that would get around that. We also know that we need to keep very high SLAs. Less than 1 second versioning time to edit a version, and less than 0.01 seconds to create a new version. And we're looking at multiple terabytes for the size of a version, so pretty quick stuff. Now, our version depth wasn't very high, but it was still an issue. So we had to keep that in mind, that it's small at 49, but enough. We quickly moved to a graph model. And here, I'll tell you a little bit why. If you make a version into a vertex, you can store all of the edits in kind of a combined area. You can also sort those by timestamp to keep an order in your versions. And then if you want to find connections between versions, you just make a parent-tree relationship, similar to how you'd handle a Git model. Here's a little diagram to walk you guys through it. So you've built a map. Patrick's the map. Patrick make edits. Patrick has a view of these edits when he pulls out from the database. A new map version is created by John. Now, John can walk up this relationship and see the higher version, right? Parent-child relationship, similar to Git. John can make his own edits on this subversion, but then when he wants to get a complete view, takes from the subversion, walks up 1 level, and combines them. Patrick can then continue making edits on the higher version with no effect to John, allowing us to separate our versions of maps while being able to stack data. This minimizes the amount of data we have to use, but allows us to still recreate maps very quickly. And this is extensible going forward, right? Mark can create things, Mark can create his edits, he can climb back up, see what he needs to. So the ability to traverse across these versions, once you take out some white space, is a graph. Nice and simple. Now, there are a lot of products out there, but we moved quickly to Neptune. And our reason why breaks down to managed by AWS. At Uber ATG, we have to iterate very quickly. We have to grow very quickly. Driverless cars is not a race that's slowing down, it's a race that's speeding up. So having someone else who can handle those servers, who already has horizontal scalable reads, vertically scalable writes, We've already got all this versioning, kind of easily modeling to Gremlin was really important to us. Our experience with Neptune has been really great. Gremlin query models very quickly to a graph. We've got a wide variety of instance types. One of the things we've looked to do is move maps of specific cities onto their own clusters. So if you've got a map of Pittsburgh, it gets its own cluster, allows us to have a really big instance type for Pittsburgh. But if you've got a map for a small city, we can make that in a tiny instance type. Save us a lot of money. And then read replication is very simple. For our workloads are bursty. And if we're going to be spending a lot of time taking out replicas, putting them back on, it's going to be a lot of wasted dev time. We're also finding that read replica propagation is coming in at under 20 milliseconds. That's the estimated time from the Neptune team, but we found it to be consistent for some pretty high loads. We're getting really fast traversals, which allows us to assemble those maps very quickly. And we've got great monitoring tools. If you ever have used a kind of more beta graph database, so you're going in there and seeing how many reads am I doing a second? How many writes? What's my memory look like in there? It's a mess. You'll get that day one in Gremlin, and you'll be able to see things as little as close as freeable memory, or how long are our queries taking? How many queries are coming in per second? So really great stuff. Some of the things you should watch there is cluster connections. If you're using a WebSocket, it's a little bit tricky, but it actually will connect you to an instance. So we had to build kind of a custom load balancer to handle connecting to a cluster and then making sure that it would distribute loads across several instances. Adding face data is faster than deleting data. If you rev up a lot of stuff and you want to get rid of it later, your timeline is going to be a little bit different. And then some of the Golang clients are still developing. We use GremGo internally at Uber, and we've got our own branch of that. But in the future, we're looking to put out something a little bit more efficient, a little bit harder. Now, at the end of the day, once we've scaled up, we have all of our map storage for all of our cities with driverless cars already on Neptune. This is only a little bit more in the petabyte data, but it can get up, had we not used this, to many petabytes of data. We've got less than 0.1 average seconds for data edits, less than 0.01 average version creation, and it's all working and running on there. Heading back to Karthik for some key takeaways.
Cool. Thank you, Yas. That was a fantastic use case. So what you heard from Yas for the Uber ATG use case, my takeaway is, again, two things, right? One, in terms of scale, Uber ATG has a requirement to process billions of relationships. The query latency needs to be in milliseconds, and they process over a petabyte of data. That's a combination of S3 and Amazon Neptune. That's a lot of high performance, low latency requirements. And the second thing is they wanted Neptune in the regions that they operate, right? And in those regions, they want to have the right size cluster. So being able to provision Neptune of the right size across the regions we are available in was also another requirement for Uber ATG. These are some of the key takeaways. With NBC Universal, if you watched presidential debates, America's Got Talent, or a Voice Vote, how many of you have seen any of these shows? Okay, quite a few. So each of those user events is being processed in Neptune, and it tends to spike. And I was just talking to a gentleman in NBC Universal that some of these spikes need to be handled within a matter of minutes. There's a voice count that's happening, and there's a small duration with which the data needs to be processed. So there's a lot of requests. In this case, it's 30K requests per second that needs to be processed by Neptune. And as they move their workload from their NoSQL database to Neptune, they saw about 40% in cost savings. And with Uber ATG, they built the microservice. You saw Yas talk about versioning of the maps. Each version a user creates is probably adding like a traffic sign or a speed limit. And that is a new version of the graph. Being able to manage that at high scale is something they're able to do with Neptune. Hopefully, these two use cases have whetted your appetite to try out Neptune and also share your journey of using Neptune in production. There are a number of sessions that we have at reInvent this week, some that have already completed, which you can catch up on YouTube, and some that are ongoing. There are also training available. If you go to awsamazon.com/Neptune, we also have a dedicated page with a bunch of developer resources, videos, tutorials, samples, you name it. There are a bunch of resources with which you can learn Neptune. And there is also an AWS training on Neptune that you can refer to. And with that, I'd like to thank every one of you for attending the session, and hopefully you gathered a lot on Amazon Neptune. Thank you.